everyone. Today we're presenting the paper titled Improving Factuality and Reasoning in LLMs Through Multi-Agent Debate. My name is Chaz, and I'm presenting this paper alongside Shaan and Lokesh. This paper was authored by Du, Lee, Taralba, Tenenbaum, and Mordach. Mordach actually works at Google Brain, with the rest of the authors coming from MIT, so it's a nice team behind this paper. To give a quick overview of our project and how we're going to be presenting this paper, we'll begin with the introduction and the background behind the paper. Then we'll discuss the motivation for a multi-agent debate, why they decided to do this, discuss some of the related works and the context behind how this works and the situation in which this emerged back in 2023 when this paper was written. Then we'll explore in more detail the methodology of multi-agent debate, as well as the experiments presented in the paper and some results, a brief demo, and then we'll go to analysis and conclusions. So to give an introduction to this, the question that's really being asked here is, what is the best way to use large language models? This paper describes some prompt engineering techniques, which is a common term these days, basically ways to kind of work the large language model to try to get better output from it. So this is addressing some of the most prevalent large language model challenges, namely hallucinations and faulty reasoning. So large language models tend to struggle with tasks like math, logic, and reasoning. And so this will be addressing those problems with large language models, as they're known to make false statements with as much confidence as they make true ones. So the motivation for this is, somewhat already been described. There's a lot of limitations when you're relying on a single model. So how can we reduce hallucinations? Well, one way would be to not rely on a single model. So this multi-agent debate reduces the dependence on any one agent, and it allows the multiple agents to collaborate and really explore more, to do a wider search, if you will, and finding the better output. So multiple model instances will generate answers independently, and then together will refine their outputs to approach something that's hopefully more true, more accurate. So some of the terminology we'll use throughout this presentation includes consensus. This is roughly analogous to convergence in the typical machine learning sense. Just when the multiple agents have come together and really agreed upon one answer, at that point the debate can stop and we can have that one answer returned. So they'll go through multiple rounds, epochs essentially, of debate, multiple iterations of this as they give their answers and then see the answers of the other agents, and we'll describe this methodology in more detail shortly. They're also able to do some self-critique or self-reflection of their own responses. And chain of thought, of course, is this methodology we've seen emerge quite a lot in the past several months. So it was still being worked on even back in 2023 when this paper was written, and they do mention chain of thought. And the cool thing about this is that chain of thought is actually completely compatible with this multi-agent debate. So there could be potentially some synergy there, and they do look at that, even though this paper was written back when chain of thought was really in its infancy. And on the right here we have a bunch of the prompts that they used for each task and the different tasks that they really checked as a benchmark for the large language models to measure their responses. So they used tasks related to arithmetic, math problems, chess, chess move validity or best move in chess. And they did that by putting the chess move into a PGN, which is a standardized text notation for chess moves. They also looked at biographies to focus on hallucinations, because it's an easy way to check if the model is coming up with quote-unquote facts that are not actually facts at all and actually hallucinations. So they did that as well by asking the model to give biographies. So this is some of the benchmarks, if you will, that they used to evaluate the models. Some of the related works and the kind of the context behind this paper. There's been, of course, a lot of developments in chain of thought since this paper was released, and these methods have a lot of synergy. They look at that in this paper. Somewhat interesting aspect of this paper as well is that they take a completely black box perspective on prompt generation, which means that completely different large language models can work together. You could have multiple instances of, say, ChatGPT, or you could have ChatGPT conversing with a Claude model, or any large language model that you want. They can work together, and there's no need to have that kind of introspection onto the internals of the model. As long as you can have the kind of black box perspective, then you can orchestrate multiple agents, if you will, together and have them do this debate, which is an interesting, approach to take. Of course, just like chain of thought, this is an extremely expensive method computationally. It also takes a lot longer to get an answer because you have to go through these multiple rounds, and they're already doing so much token generation anyways, and these are streaming in, and it's going to be a lot of time that you have to wait compared to an ordinary LLM, task. So chain of thought is of course expensive as well. Then when these models go along with long chains of thoughts before they come up with their output, and this methodology takes it even a step further and allows them to go in multiple debate rounds and stretching that prompt out very long, going through multiple prompts, really just for one answer. So it blows up the amount of computational expense that's going on here, which is already a concern with large language models in the first place. So that's certainly something to be aware of as kind of a limitation of this paper. And to briefly give a kind of overview of the actual multi-agent debate process, it begins with the user query, which is related to one of the benchmarks mentioned earlier. So it might be asking, what is the next best chess move, or to give it biography, or a question from one of the other benchmarks that's used for large language models. And each agent will respond to this question individually at first. And then the agents are given access to the other responses of the other agents. And based on this new input, they're asked to refine their answers. And this is what goes on in a debate round. And they'll do this over and over again, seeing each other's responses and responding to them, so on and so forth, until each agent is roughly in agreement and has reached consensus. So how do you know when they've reached consensus? Well, convergence is not guaranteed here, but they found that it usually happens. They also found that with some tweaks to the way they actually instruct the models to act, that asking them to be stubborn and have longer debates yielded the most accurate results. So they do explore some different ways to really look at how we can set up these agents and how we can instruct them to act to get the most effective answers at the end of this debate. And now I'll pass it off to Shaan, who'll go into the rest of the paper.
Thank you, Chaz, for the introduction. My name is Shaan, and I'll be jumping straight into the methodology and technical explanation. So starting off, we'll go over the overview of the debate process itself, which includes the initial answer generation, the multiple rounds of review and updating from the model, and then the final consensus answer, and different ways that we can actually get to that consensus answer. Some of the technical details that we'll be delving into is the explanation of the prompt structure itself, as prompt engineering in multi-agent debate is extremely important, the definitions of both variables, parameters, and hyperparameters, as well as going over visual aids. And these detailed diagrams will be showing not just the flow of individual answers, but the actual results from this research paper. So looking at the methodology and technical explanation, as you can see in figure 26, we are looking at the actual multi-agent debate in progress. And in this case, we're looking at the example of chess. So kind of looking at a closer look at this, we can see that we have 3 rounds of debate. And in each round, we are given an instruction. This instruction for the first round includes the set and the possibility of the question itself. So for round 1, since we're using the case of possible chess moves and we're trying to find the most optimal move, we give the current sequence of chess positions, which corresponds to all of the concurrent pieces of your pieces and the opponent's pieces. Then we prompt the agent, and in this case, we're actually using 2 agents. And these agents are given the instruction of use the solutions from other agents as additional information, but still try to solve the main instruction. So even though in round 1, we have no additional information from past agents, we're still using the information given in the instructions. Then you can see in round 1, we're given 2 different outputs from each agent. One is saying to move dx e6, the other one is saying bishop to e3. Now, in round 2, we synthesize those results and we again provide the initial instructions from before, but also append the output from round 1. What this append does is make the agents think through each of each other's responses and have some type of, not necessarily chain of thought, but some thought about which answer is correct. And the same is repeated in round three, but since round three is our final round, we end up with something or called convergence, which is when both of the answers congregate together and you get the same queen to a4, which in this case was the best move. And something to note is that yes, we went over the initial answer generation, but in this case, we only had three static rounds. Sometimes an augmentation to multi-agent debate would have having dynamic rounds. So maybe you could say until both agents reach convergence, convergence being having the same answer, to keep running each round over and over again. Okay, moving on into the technical deep dive. Some of the variables and parameters that I talked about were the number of rounds, which is a hyperparameter, the number of agents, again, another hyperparameter, and the prompt verbiage. And the prompt verbiage not being necessarily a quantitative measure, as we can see in this example prompt, where two different prompts right here basically dictated how long the output would be in terms of the debate. So this could not only mitigate a lot of loss in hallucinations, but it could also control how large our output's going to be. As you can see with just these three examples, the amount of information being passed in after each round can get to a very, very large output, maybe hitting some type of token limit if we're not careful. So some of the characteristics we have is, like I said, the debate length, but also the agreeableness. And this agreeableness, Lokesh will talk about later, but it mainly characterizes how willing each model is to get to convergence between both agents. And looking at the short versus long debate prompts, we can see that performance actually increases as the debate goes on for longer, and each long debate prompt is increased. Now, looking at the actual accuracy of this multi-agent approach, so we can first see that the result itself is increased as the number of agents is increased, thus meaning that the more agents you have, typically the better results and the better accuracy you'll have. This specifically is looking at a math data set for a popular eighth grade data set. And in B, you can see that as the amount of debate rounds increase, also accuracy increases. But unfortunately, this model and this architecture also falls short in the fact that there is diminishing returns. So the increase from round two to round three is not as drastic as the difference between round three and round four. So the results in analysis. Basically, what we've looked at thus far is a chess data set and the math data set. The math data set, again, being that eighth grade arithmetic. But another data set that this paper looked into was biographies, actually validating not just accuracy, but memory and information recognition and recollection. So some quantitative results that we'll be going over is tables 1 and 2 within the paper, as well as the difference between summarization versus concatenation. So some of the results that this paper presented was the difference between one-shot prompts to this multi-agent approach. One-shot prompts being just typing in and supplying the normal instructions into a LLM, and multi-agent approach obviously being the tiered round system that we previously talked about. So in table 1, we look at the multi-agent debate on improving reasoning itself. And looking at just purely the math on this, you can obviously see that at the time in 2023, the state-of-the-art model being GPT 3.5 Turbo, the multi-agent debate has a significantly higher rate of reasoning on both arithmetic, grade school math, and in chess. And the same can also be said about factual accuracy. And this factual accuracy was measured mainly on the biographies I talked about in the past, but also in chess move validity, as it had to remember the previous positions of the board and how they interact with one another. To further show this, you can see that the multi-agent debate also is improving accuracy across all of these different data sets, and there's a drastic increase in accuracy among all of them. Now, in traditional multi-agent debates, we would just concat each of the rounds and outputs of each agent onto the next one. But like I talked about in the past, where we may hit a token limit if we're not careful of the amount of rounds or the amount of agents output, We can use summarization to still include the main key points behind each of the agent synthesis and discoveries while still staying under that token limit and allowing for more rounds of synthesis and discussion between the agents. Next, we'll be jumping into the demo of multi-agent debate. So I'll see you there.
Okay, so now we're jumping into the demo. So for the one-shot approach, as you can see when we get the one-shot answer, we get that the answer is 192 square units with only one prompt. And here, as you can see, we can enter the number of rounds as a hyperparameter. And again, this math question is testing the logic. And as you can see in the output, when it finishes loading, that we have two rounds. Round one has the output from agent one. Round two has again the output from agent one, but we also have the output from agent two and the moderator in both. And finally, in the final synthesis, we get the answer that it's 192, given all of the previous information. And next, we'll be looking at a legal use case, with the question being, how might the interpretation of the Fourth Amendment adapt to modern surveillance challenges? So in the one-shot answer, we get an answer around 400 to 300 characters long. And the debate approach, I've now set the parameter to 3 to show that the number of rounds we can dynamically or statically increase. And as it loads, we get to see that we have round 1 with agent 1's output, round 2, the moderator, round 2 with the agent 1, and agent 2 again with the moderator, and finally in round 3 we have one final moderator in the final synthesis. And as you can see, this chunk of text seems pretty blocky, which is why instead of concatenation, we may use some type of summarization to take all of the information from each of the rounds to then supply to the final synthesis. Thank you. Now passing it off to Lokesh.
Thank you, Shaan. Now I'm gonna go debate versus the chain of thought approaches that were discussed in the paper. And in a bit, we're gonna go over the demos. So by definition, the chain of thought models are employed by a single large language model where they are used to infer step-by-step reasoning process similar to how humans solve the process. So it's much more similar to the human reasoning, apparently. So it doesn't just give the final answer, but it also gives us the intermediate stage where how it got to the answer. While it comes to the multi-agent debate, it utilizes multiple language models to debate among themselves as in agents, akin to a panel of experts. From the previous slides, we might infer that it reduces hallucinations and improves the factual accuracy through debate and consensus reaching techniques. So they had performed an experiment. So if we see the figure 6 in the paper, where they had integrated the synergies with other methods, where they had integrated chain of thought into single agent and multi-agent debates, where the single agent debates being the older response is fed into the contemporary prompt. So as we could see, the performance had substantially increased when the chain of thought is integrated into the models. So the accuracy is computed over GSM 8K dataset, which is verbal middle school problem dataset. So if we go over to the demo, the researchers had created an multi-agent debate model, which is called LLM Agora, and they had implemented it on Hugging Face. So we'll just take a quick look into the demo. So they had used ChatGPT as the summarizer for each and every open source model. So they're like using a bunch of open source models. So for the day, we are gonna pick Llama 2, Wizard LM, and Okra. The later ones are Hugging Face's open source models, which each of one being 13 billion parameters. And these are like the legacy models from 2022. So if we see, we are going over the math dataset along with the chain of thought option, and we're gonna try to ask a basic BODMAS question from the middle school math where they needs to perform multiplication in the first place and later add or subtract the terms. So if we could see, Llama had given us chunk in the very first go, and Wizard LM has given us 152, and Okra has given us 342. So the summarization from ChatGPT would be obvious for this case. And this is the zero-shot summary. Later, the summary is fed into each and every agent. So using this knowledge, they would infer again and try to debate among themselves. So in this case, they are trying to explain how they are arriving at the answer, but still it's factually incorrect. So again, Llama had produced a chunk answer, which is 1, and then the Wizard LM had produced 342, and Okra had produced 335. And then later on the round 3, Llama is still 1 and it's stubborn, but Wizard LM had changed its answer to 184. And then later, Okra's answer is 335. So if we look at the performance curves, the performance with a chain of thought is substantially better when compared to using traditional models without the chain of thought in the math and verbal problems perspective. So we could see it from the results where it's static until the second response, but it had taken up or increased a bit from the third response. So the method had showed that language models can get better at math and strategy problem by working together. And it becomes relatively a little bit more better if chain of thought is induced into the models. So the model also helped to reduce the number of wrong or made up answers by doing self-introspection or debate with other agents. Heading over to the next slide, where we compare the 2023 models or 2023 legacy models with the contemporary chain of thought models. So as we all know, it's a fast-moving space, and the advances are going in a rocket speed. So we'll just take a quick look into the demo where we are using DeepSeek model. So on the very first go, we had asked our verbal question, and then it has thought about it and inferred the answer, and then it has a bunch of intermediate steps and explanations of how it arrived at the answer, and later it has produced the answer of 192 square units, which is factually correct in this context. And later, we had also asked the legal question where how might the implementation of Fourth Amendment adapt to the model surveillance challenges? So likewise, to the math question, it has also inferred it from the chain of thought approach where it has compared it with a bunch of citations, and then it has weighed pros and cons, and then gave us the answer, which is technically and factually correct, but it's still its option on a legal case or standpoint. And then we had our question from the previous comparison the same BODMAS question that we compared it with a 2023 chain of thought models where DeepSeek 2025's model, which is the state-of-art model of current day, has outranked it, and it's substantially better and accurate when compared to the previous legacy generations of the chain of thought models. So it has deepened the reasoning and improved the coherence of the models. So this has allowed the models to tackle intricate tasks that were previously beyond the capabilities of the large language models. So it has increased the reasoning abilities of the language models. And then this led to more reliable and trustworthy outputs, especially in the tasks requiring complex logical deductions or problem solvings, as we had already seen in the demo. So heading over to the analysis and discussion, impact of the key variables. So in the bunch of experiments that we had performed, the key variables being the number of agents, where it increases whenever the number of agents increase, the performance had enhanced, but the improvements diminish as more agents are added. Similarly, increasing the number of debate rounds boosts the performance, though the gains plateau after approximately 4 rounds in the context of the experiments that were performed in the paper. Coming to the strengths of the work, it has improved the reasoning consistency and factual accuracy. Coming to the limitations of the work, running multiple agents and debate rounds increases the computational cost, complicates the prompt design, while you need to fine-tune each and every prompt and try to add it whenever you might want to go over multiple rounds in a debate process. And then it might also lead to convergence issues or incorrect answers. So as we had also discussed, even though all the agents come to the consensus, there is no confidence that it might be factually correct. Coming to the future considerations, the future involvements include exploring new debate strategies like allowing agents to express uncertainty, or summarizing the debate history for better focus, and integrating diverse large language models for more robust discussions. So let's head over to conclusions and future directions of the work. So the multi-agent debate enhances the large language model reasoning and factual consistency. When we consider the future works, we could include the advanced prompting, or we could further explore the agreeableness, which is possibly due to the instruction tuning or fine tuning of the prompts, or the innate reinforcement learning based on the human feedback that large language models do day to day. So we could make agreeableness as a metric and try to use it as a sigmoid function or an activation function if at all a agent is not confident enough on its answers. So it could act as inverse of confidence, where it could be less stubborn if at all it's not confident. And we could also try multiple uh, techniques like changing words in a prompt to help large language model to change its mind or stand in its group, or else we could also achieve it by using sentiment analysis, or we could also explore new debate strategies like allowing agents to express uncertainty, as we discussed before. So coming to the conclusion, the multi-agent debate significantly enhances the reasoning and factual accuracy of the large language models by leveraging the power of debate and consensus among the multiple agents. So this is the takeaway of the whole presentation for the day. Thank you all. Be open for your questions.